Yes. So now, Jesper, yeah, we are online again.
Okay.
And I'm sorry about that.
Okay, guys, we continue. I don't know if you know the nutrient patterns in oceans. You see it for barium, you see it for zinc, for example. But as I told you before, the main factors controlling cadmium is remineralization of organic matters, which enrich the cadmium at the bottom here, and uptake by phytoplankton declines cadmium in seawater, the cadmium concentration, and vice versa for the cadmium isotopes, where remineralization enriches the seawater in the lighter isotopes at the bottom waters, and uptake of the light isotopes in the surface waters will enriches the seawater in the heavy isotopes. So, as I said, overall cadmium acts like a nutrient element. This is the first paper from my PhD, cadmium isotopes in Bahamas platform carbonates, a base for reconstruction of past surface water bioproductivity and their link with chromium isotopes. The focus of that study was to constrain variations in cadmium concentration and cadmium isotope values in modern carbonate platform and investigate the effect of diagenetic processes. And then we want to compare the variability in cadmium isotope values versus chromium isotopes. The main goal was to establish a double tracer that is potentially capable of providing information regarding the interrelationship between surface water redox and primary productivity, which potentially could be applied to ancient carbonates. So here's the profile of Bahamas with different lithology, and here we have cadmium isotopes and chromium isotopes. The chromium are the circle ones. I don't know, it's difficult to see, it's a little figure I can see, and the diamond forms are cadmium. The red ones are aragonite samples, and the blue ones are calcite samples. The yellow ones are we decided to, we don't have phosphate data from these samples, so but they have rare earth elements patterns that definitely looks like it could be phosphate. But it's from early Pliocene to Holocene, and it's very cold. So, as you can see, the average cadmium in the aragonite-rich samples, which is the red ones, are lower than in the calcite samples. And enrichment of cadmium is the so-called deviates, and this might relate to phosphates. We cannot see any changes in the 114 cadmium values during the entire core. It's they are very you can see these. It's just they are all within the range of the deviation. So we could see that the core we have a transformation during the core downward from aragonite to calcite, which is related to diagenesis. And as you can see at figure 1, we have manganese here, we have strontium here, that there is direct link between these two elements, which confirm that it's a diagenesis. Also, the link between strontium and the carbonate minerals. We have the aragonite calcite ratio here, and strontium up here, and there's also a clear link between these. I did the same with the manganese on the y-axis and aragonite calcite on the x-axis, and there's also a link between. But there's no direct link between, except for you can see that there is a small minor enrichment in cadmium in the calcite-rich samples compared to the aragonite-rich samples. And this enrichment we link to the incorporation of cadmium into the calcite, which is more preferable than in aragonite. Then we tested the trital effect of on cadmium, and we used aluminium as an indicator. And as you can see, it's just like a buckshot. There's no link at all between cadmium, the raw cadmium, and the aluminium. So. And then we used a special formula that is also used for chromium to calculate the trital effect on cadmium, and as you can see, it's less than 1.01, 0.01 per mil. So we haven't made any correction to our cadmium. So then we also tested the cadmium versus chromium, and the chromium was made from a previous study by Kleve et al. And we have a correlation between chromium and cadmium in the aragonite and calcite samples. Maybe also in the phosphate, but we decided not to investigate more on this because we don't have the phosphate data. But we interpreted this as that the correlation between cadmium and chromium indicates the same type of process that incorporates cadmium and chromium into the mineral. But we don't have any correlation between the two isotope systems, and this is because cadmium reflects the bioproductivity effect, and chromium is redox sensitive and is more related to the manganese and serial numbers. So to read the cadmium isotopes, we need to know that there is an offset from seawater into calcite of 0.45 per mil, and this gives us this is the raw data, and this is the corrected data, and it shows that all samples are statistically within the Northern Atlantic surface seawater. And we were very happy about that because they should be in that range. So the third and last paper from my PhD work, which is almost ready for submission, regarding the Danish basin across the Cretaceous Paleogene boundary, which is the first study of combined cadmium and chromium from 3 carbonate sections, Stevens Cliff, Nuclear, and Woodstock, all of them in the Danish basin, and all of them regarding the Cretaceous Paleogene boundary. So the main goals was again test the double trace of cadmium and chromium, and correlate the double trace to the possible collapse of bioproductivity across that boundary. Then we want to test the mineralogical changes on the cadmium isotope signature and on the cadmium concentration. So a little bit background story, since I guess many of you haven't heard so much about the Danish basin. So the Danish basin was placed here. Maybe you can see the red stars. And it was situated 45 degrees north across the boundary, and it has connected. It was connected to the intercontinental sea here, and to the Boreal Sea, and to the Tethys in the south. During late Cretaceous, the sea level in the Danish basin was approximately 300 meters higher than today, and the seabed was mainly covered by nano and microfossils, calcareous fossils, and that indicates really high bioproductivity. The 3 sections are from here and from Stevens Cliff. Copenhagen is now. It's a really small country. And the Cretaceous Paleogene boundary is representing one of the 5 major extinctions during Earth's history. Also because of major volcanism from somewhere around here, and the meteorite in Mexico. So the 3 sections are here, and the Cretaceous Paleogene boundary is this straight line around here. And this I will not say so much about. This is a marl that represent the late Cretaceous warm matter. This part, and this part, and this, all of this, it's unidentified coccolith dominant late Cretaceous particular, and it's very homogeneous. Then only in Stevens Cliff we have an unidentified stratigraphy within increasing of the abundance of bryozoans. And here is the very famous fish clay. It is represented in all three sections and is very rich in detritus. Then also only in stone split we have a lithified ceritium limestone, and ceritium is and then on top in all sections, no, only in nuclear and in stem split, we have bryozoan dominant stratigraphy in the danium. The triton materials and samples, as you can see, this is a plot between titanium and aluminum, and the black ones, which is all of these, are the detrital influence samples, and the gray ones are the carbonate samples. So we can see that there's no correlation between aluminium and titanium in carbonate samples, but there's a strong correlation of a squared regression of 0.9 in the fish clay and in the critical gold mark. Due to the abundance of titanium in these sections, we have favored titanium instead of aluminium, because aluminium was simply too high. So some of the samples we had to correct, so we got the negative chromium values, so negative chromium concentrations, and you cannot have a negative chromium concentration. Then we used yttrium-holmium ratios in the fish clay samples, which is the brown ones, and they show also that this is definitely not from seawater. There's definitely some other elements that are influenced in these samples. So we only have a minor influence on the samples in the bryozoan limestones, and no or minor influence on the critical gold marks. And the detrital effect also plotted here with cadmium against titanium and cadmium isotopes. And you can see there's a strong correlation between titanium and cadmium in the detrital influence samples, which is the fish clay and the critical gold mark. But we have no correlation between the carbonate samples. And the detrital fraction is actually less than 0.2%. The detrital cadmium fraction. And if we look at the cadmium isotopes, we have no or minor detrital effect on the cadmium isotopes. And if we only look at the brown samples, we can see that there are high abundance of titanium, and they are all around 0 in fractionation, which correspond to the continental crust, which is about plus 0.08. So cadmium and chromium in the three sections, we can, this is cadmium concentration, chromium concentration, and cadmium isotopes, and chromium isotopes. So this we can see is that actually very homogeneous of both cadmium and chromium. We have the curiform here, which is a little special, but the rest is actually very homogeneous. Regarding to the isotopic composition, we can see that it's the same. However, we have some small fluctuation in steric but this is because this becomes more, this bed is more rich in organic matter. But we can see in the chromium isotopes that they start actually, is also only in steric. They start already here when the amount of organic matter starts to increase. We can see that the chromium isotope starts to be less fractionated. It becomes more complicated when we comes above the boundary. There you can see it's very fluctuating, and this we can actually not explain at the moment. We need to do some more investigation on this. We also can see that there's a high enrichment of cadmium and chromium in the fish plate, which corresponds to the triangle effect, or maybe phosphate, because phosphate is very rich in these samples also. And we know that's why it's called fish plate, because there's a lot of fish bones in these layers, and it's very compact. Yeah. Then we can see, especially in the cadmium isotopes, we can see that across the boundary there's a negative shift, and we can see that in all of the sections there's a negative shift in all the sections, and this is regarding to this heavy change in bioproductivity across the boundary. As I said, this negative shift we have before the boundary in the chromium isotopes, we have related to the Deccan traps changes, and which actually change the ocean's oxidation states. These fluctuations that we see above the boundary might be the regeneration of life and bioproductivity. We don't know yet, but we know that the bioproductivity, of course, after the boundary varies a lot. A lot of species get extinct, and a lot of new species occurs. So and it's both nano and microfossils. Thanks. And if you have any questions, you can ask them in Portuguese, then he will translate.
I understand the questions. So thank you, Jasper, for the nice talk, and I hope with cadmium we can start to answer this difficult question of trying to quantify ancient bioproductivity.
Yeah.
And maybe link that with all those hypotheses of bioproductivity.
I hope so. We have one of them.
Quer que eu faça em português? Pode fazer em inglês?
Quer tentar? Thank you.
Well, Jesper, thank you for your presentation. I'm actually a biologist, so I would like to see you explain a little bit of the bioproductivity at the end. We saw in the both curves. We can see that the graph goes down, and as you said, it might be because of the event of the extinction, like going back. But there's any other hypothesis other than what you guys are saying about the upwellings and other.
So what is the question?
Não consegui fazer. Me perdi também, mas tem que o Jefferson. Queria saber, basicamente, como biólogo, já que ele falou que está linkado o trabalho com o upwelling ali, com a ressurgência, se tem alguma outra linha que eles estão seguindo, ou se é realmente essa de que vai ter essas ressurgências e aí está associada essa questão do cadmio do titânio, dessa baixa logo após o evento de extinção, e aí a alta, se isso daí está realmente associado com a explosão de vida, com a multiplicação de uma nova forma de vida.
So try to maybe condense that.
Eu sou muito prolixo também.
No, it's okay. Yeah, it's good. Is upwelling the only explanation for the cadmium bursts there, the peaks, and after extinction, like explosion of life forms, would that increase bioproductivity as well, or upwelling is the answer always?
No, answer. Upwelling is not the only answer, but it seems like to all the studies that have been published at the moment, it seems like cadmium isotopes are very much related to bioproductivity. Yeah.
So, sim, que está correlacionado e que o evento tem.
So I think
as I could see, those are probably correlated events, but you can't say for sure with the data you have now.
No, because the study of cadmium isotopes are very new. So, yeah, it's very new. So we are only making it's experiments, but it seems like our experiments fits with bioproductivity.
So I think this is something that's important to stress. They're developing this proxy now in the same lab as Robert Fry and his students developed the chromium isotopes for oxygenation. Now they're developing the cadmium isotopes for bioproductivity. So the work of Jesper is very important because this will lay the grounds, the foundation of people that want to try this proxy for other stuff and then test it. So that's why he had that many graphs, like trying to show if cadmium is varying with aluminium, which is a detrital proxy, and titanium, and if it's varying with the chromium, and if it's varying from aragonites to calcite, if your rock is suffering diagenesis. So this kind of like making all of the test work for people that are going to come later, and then you can apply that to these nice sections in the Danish beaches.
Yeah.
I think so, right?
Yeah.
Cliffs, yeah, the cliffs in Danish beaches, like barreiras, and then where you have the KPG boundary, so it's a very important boundary. Yeah. And one thing that I think is clear, that you look to it and you see that in the KPG boundary you have variation in cadmium, right? So it's probably telling you something. What exactly that is, probably related to bioproductivity, but
yeah.
And Claudio will have a question, sorry.
Yeah.
Yes, what are the lowest values that you get at the KT boundary?
The lowest cadmium
Cadmium isotopes.
they are around 0.
0. So
Yeah.
that nadir is
No,
0?
but after the boundary,
Yeah, after that.
yeah,
one.
that's minus 0.3.
So it's lower than the input from the crust?
Yeah.
How we explain that?
This we don't know how to explain. First, I was thinking that this negative peak could be related to new species of bryozoans, but this but the bryozoans,
Vital effect.
yeah, but the bryozoans, they after I did some extra experiments, the bryozoans, they increased higher. So I don't think it has something to do with bryozoans. Yeah, we don't know. We don't know why it's so negative there, because we only have 2 negative peaks in the nuclear section, and it's more, around 0 in nuclear, where in stone flint it really are negative. But also much higher resolution there. I think I had many more samples from stone flint than I had from nuclear. Yeah.
So Jesper, one thing that might be interesting, like this bioproductivity bursts, they are more related to algae or bacteria or something like that, or you specifically, like you can, if you have eukaryotes or metazoans, they're gonna be reflected, or is mostly like algae that's causing this burst, like the primary producers?
Yeah. Yeah.
Mostly the primary.
Yeah.
So I think this is an important point, because as Andrea was asking, if the bioproductivity burst has something to do with biodiversification, but actually there are zones where you have eutrophication. Like you have a burst in algae, but you're actually killing everything that's below it. So you might have like bioproductivity pools, but that doesn't really translate to biodiversification.
Yeah.
You might have had like an algal bloom or something that
Yeah.
is very good for algae, but very bad for everything else.
Yeah.
Yeah, you probably use that to trace.
And we actually don't know any kind of what different species, how they fractionate cadmium. We don't know that yet, because that could also be really interesting.
You're probably gonna have someone to have an aquarium or something that have snails and fishes, and
Yeah.
you try to see
Yeah.
how they are eating the different cadmium.
Yeah.
People do that. Start with okay. That's the story.
Any other questions?
So thanks again, Jesper. Very good. Pessoal, agora a gente vai passar para a palestra da
Calter, né? Só que essa palestra que a Calter vai dar agora, ela faz parte acabou fazendo parte também desse grupo de palestras de convidados, mas ela também vai ser a primeira palestra de uma série especial da pós-graduação, por isso eu chamar as meninas aqui, Janaína e Mariana, para dar essa introdução. E eu também queria que a gente agradecesse aqui o pessoal que está fazendo acontecer a infraestrutura aqui complicadíssima da história, né? Suzana, Mariana, e o Lucas, todos mais que ajudaram, tem mais gente ajudando também, né? Equipamento, com tudo, então, Ana Clara, né? Todo mundo está por aí, então, salve para eles também, que eles fizeram para conseguir.
Bom, gente, eu sou a Mariana, a Ingrid e a Janaína. Eu sou uma das representantes, né, da pós-graduação, representante docente lá no colegiado. E a gente está iniciando essa série de encontros que a gente está chamando de Divulga Pós hoje. Então, muito obrigada por ter recebido a gente também no evento. Acho que foi bastante legal. Obrigada a todos os palestras e o pessoal da organização. acabou ajudando também bastante nessa parte. E essa série de encontros, a proposta é que a gente se reúna mais ou menos em torno de uma vez ao mês, então a gente está começando no início agora de abril, o próximo vai ser no início de maio, para a gente debater questões em relação à pós-graduação. É aberto, então os alunos da graduação, se quiserem comparecer, também tirar dúvidas, conversar. E a gente começa com a ideia de cada um, né, num desses encontros, apresentar um pouco sobre o que está fazendo, mas eventualmente a gente pode trazer mesas de discussão, levantar dúvidas, né, sair e aí é isso. Então, esse de hoje, esse primeiro, eu queria agradecer a Calder, que aí ela vai fazer a abertura. A Calder é pós-doc aqui do programa. Os outros pós-docs também estão convidados, né? Quem tiver interesse de vir um dia no próximo, por exemplo, falar, a gente se organiza, se for um, se for dois, dependendo do tema, mas está aberto aí para a comunidade. Então, agradecer a Calder que vai começar, né? E as meninas que
eu acho que a ideia assim, é a gente estreitar a relação, né? Principalmente entre os estudantes, que às vezes a gente só conhece o trabalho do outro na semana da pós. E às vezes a gente está trabalhando com coisas semelhantes, tem experiência, pode trocar, né, figurinhas. Então, a ideia é a gente conversar mais, se aproximar, né, participar com sugestões para o programa. Então, é isso, essa informação.
Está aberto para a comunidade dos docentes, né?
A gente também tem a ideia de ser uma coisa bastante colaborativa, tanto em relação à pesquisa um do outro, quanto das coisas mais simples, botar o dia que você prefere. Por exemplo, a gente tem a opção de ser toda segunda-feira, mas às vezes na segunda-feira a maioria das pessoas não vão poder. Então a gente vai ter essa opção também de ser algo colaborativo mesmo, seja aberto para todos.
A intenção é que seja tem essa periodicidade de um mês, uma vez ao mês, no início do mês, mas está aberto para colaborar e precisar de auxílio, né?
Hello everyone, so my name is Kauthar. I come from Algeria and I'm a postdoc student here under the supervision of Professor Projeto. Today I will be talking about the geology of the Volga Mountains in the Sahara Desert, but more specifically in Algeria. So just so you know, Algeria is very different from the real name. The real name is El Jazair. So El Jazair and Algeria are quite different. But that's just like information. And also, Hogar is Ahgar in the local language. Anyway, so before starting this presentation, I would like first to show you where Algeria is. Most of the time people know where Morocco is, where Tunisia is, but they tend to forget this big country in the middle, right? So here's Algeria, please remember, okay? The big country between Algeria and Tunisia. And also we're very proud also, all the time we tend to say, oh, Algeria is 5 times France. So now you have good information to remember where Algeria is. Alright, yeah. So I've been talking to some colleagues and students here and I realized how different our field trips are. The conditions, the challenges are very different. The time we spend there also is very different. So I'll just give a quick overview of how things happen there. I think it's quite important because a lot of times we start our PhD or our master's degree with a specific title, okay? But at the end, when we are here to defend, it's a completely different one. And people are very curious. It's hard for people outside Algeria to understand why we have this problem. So first of all, you need to know that when you go to the desert, there are times where you are within days from a village or from a city. So for safety reasons, usually however big or small your team is, you need a minimum 2 cars to go there. Because if there's a problem with one of the cars, you need another one to get back, or to get help. So, and that's a lot of money, because cars are kind of really expensive for those, areas. Also, you can never assume to go alone there by yourself. You need someone from that area, and we call those people the Tuareg people. I don't know if you've ever seen those people wearing scarves around their head, and those people, believe me, they are better than your GPS. So forget about your GPS. When you get there, if they tell you to take one road instead of another, just believe them. One of the reasons is because we have no knowledge about sand dunes, all right? Now, in their dialect, they have this, they actually make the difference between what they call dead and alive sand dunes. So what's the difference? When they're dead, they're quite compact. So you can walk on them, you can get by car on top of them, and you're safe. What they call the alive ones is that they're not compact enough, and if you go on top of the car, you can slightly just, get in. And that's really hard because nobody's there to help you, and as I said, you are within days from a village or a city. Also, the other thing is that you have to think about gasoline, right? If you're away from a gas station, so you need all of that at the back of your car. And that's why also you need 2 cars. One is never enough. You have to think about food supply, water supply, and that's a big deal because sometimes it's too hot and you drink more than you have. And I'll show you some pictures of how you're supposed to get water. And that's why you can never go alone. People from the north cannot go alone in the south. It's impossible. It's quite impossible. So here I'm showing you what we call their wed, or people call wedi. So what is a wed? Wed is a stream bed that is most of the time dry, except during rainy seasons. So here also these are quite dangerous because as you see there are a lot of mud on top, and if ever you're caught in the middle of a rain, your car can get actually taken away from the rain. And from that wed, like you're in the middle of a valley. And a lot of people died actually because of this. So you always have to be careful to choose the time of the year that you go there. And usually it's between November and the first part of March. Because after March, you start having those sandstorms. And they are very, very frustrating and very dangerous as well. And sometimes, like if you stretch your hand this much, it's impossible to see your hand. So let alone the outcrops or your pampas or whatever. So you really have to be careful when you go there. And another thing is like sometimes, so yeah, I forgot to mention that you don't have paved roads, okay? This is your road. This stream bed is your road. So sometimes you go and it's quite wide like this, so you're just driving and everything's cool and everything's great. And then the more you carry on, and then it gets narrower. And so what do you have to do? You go back and you take another path. Sometimes you're driving, but some outcrops and some rocks fell, and that's like impossible to overcome. So again, we waste a lot of, what I'm trying to say is that we waste a lot of time trying to get to the outcrop you want, Yeah, maybe, so that's one thing. Yeah, so I was talking about when you're out of water, right? You have to look for wells. Now, water wells they have a strategy actually. So if you have 2 ranges like this, okay, you're in the middle of a valley, they usually pile up many stones on top of those ranges. And when you see those piled rocks, know that in the middle, at the intersection, there's a well. So if you're out of water, just try to look up the mountains and look for piled up rocks. That would really help you. But there are other times, should I press here? Oh, yeah. But as you see here, this is not an installed wall. So sometimes we're just driving and then they would tell you, oh, we have to stop. Why? There's water here. And we have no idea. Actually, we cannot understand how they know. They just know. So they just have to dig a little and you have some clear water coming up. And that's amazing. And it's a really good water. So that's why I would never emphasize enough on going with local people. They know this land better than anyone. Oh, I was talking about sandstorms. So here are a couple of pictures here. I don't know if it's neat enough to see, but like people standing here, it's impossible to see the outcrop, right? And here it's the same. The visibility is completely, it's impossible to see anything here. All right, so there's another challenge. And this one is more frustrating, at least for me. So actually, before you go to your field trip, like you prepare everything, you've got everything done. You know, you have your GPS positions, you talk to your colleagues or your professors, but once you get there, you're facing another reality. It's completely like different from what you see on a map. And the first thing is that sometimes, as here, I had a friend who once needed to sample some sedimentary rocks. On the map, everything seemed okay, but once we arrived there, we just realized how high it was and how the slope was so steep. And like there was no way for us to go up there unless we like camped for many days there. So, and as like you have so many challenges, so you have to choose your battle. Do you want to go up there and sample, or do you want to go continue and find something else to do? So you really have to balance time and your targets. What is really a priority for you? All right. On the second one, so I was trying to sample a granite, and it was really huge on the map, and I was so happy because you know they were like really interesting geophysical signatures. And then when I got there, we just had this. It was like a granitic arena, you know? So it was just like really thick sand, and this was mapped as a granite. So it's crazy, but yeah, it happens a lot. And yeah, this picture just to show that most of the time, after a sandstorm, you're not looking at your outcrops the same way. Sometimes you're just walking on top of them, you know? And that makes it hard to sample, to find a good sample, you know, something that you can do with. So you're just walking on top of them. And unless we could do like drill holes, which we don't do, unfortunately, you can't know what's under there, really. And as you see here are beautiful marbles, but what could you possibly sample from this? It's really weathered and like you have small pieces. So again, you have to carry on and think about something else to do. Oh, I wanted to show this, like this outcrop, before a sandstorm was completely visible. The outcrop as well. We could actually like draw the sketches, you know. We could sample, but after just a small sandstorm, like we had all this side covered. And sometimes it could be completely covered. This is like a couple of days later. So it's really a challenge. And we had a lot of friends who had specific GPS positions, you know, for specific outcrops. But when they went there, they were just sand. Probably because the outcrop itself has been covered with sand. So you just have to respect nature, right? You can't choose. You don't do it your way. You do it the way nature wants. But the good thing is like you can encounter really cute animals that you don't see in the north. And so there are some wild goats, some quiet lizards, and this one I don't know the name of really. And we have birds. So there's a specific bird with a white head we call mula mula. And we are very happy when you encounter those because, you know, if you find a mula mula, there's water really nearby. So this is good for you, right? Of course, the landscapes are amazing. We have some camping all the time. And as you see, we also learn how people in the desert cook. So they cook, as you see here, they're cooking bread between, covered with on top of the sand, covered with fire. Yeah, well, of course, there would be some sand in your food. But you also have some really delicious tea after that, and it helps a lot with digestion. So just go ahead and eat. Okay, so at the beginning, I showed you the position of Algeria and in respect with Brazil, okay? So since Permian to Jurassic time, we had a common history. We were all part of the West Gondwana geology, yeah, let's say. as you see, Africa has two influences. The one with the South American plate, and the second one is with the Eurasian plate. Our biggest problem nowadays is the Eurasian plate, because there's a convergence, and the north part became very seismic, and it's been quite dangerous actually, because the magnitude gets higher each year. The reason I'm saying this is, like, if you look at this geological map, you would see that while the south part is affected by old orogenies, alright? You can see at the ages, it gets younger. The more you get to the north, the younger they get. And yeah, that was I'm trying to be brief here. Alright, so here are the main units or domains, geological domains we have in Algeria. In the south, so we have the Hogar Mountains, and then we have the Atlantic Mountains in the north. And this is like the original, the Atlantic orogeny, so it's the Alpine orogeny. And between both, we have a platform. All of this is actually sand. This is a desert. What you need to know is that the Sahara Desert actually occupies more than 70% of the country. And here is like a cross-section, a really quick one. The scales are not respected, of course, but here all this would be considered as the northern of Algeria and the southern part. Here starts the Sahara Desert. Between both, we have a really huge lithospheric accident. It's called Sudatlasik, like it's a Southern Atlas accident. Alright, so here I just wanted to show, I wanted you to have like an image of how the relief is with a gray scale. Everything you see in gray here are the reliefs, so the mountains. And all the rest is desert, is sand. So whenever we want to go, my university is here in the north, okay, it's in Algiers. And we have to go all down way here. The capital of the Hogar is Tamanrasset, okay? This is like your last chance to get medication, to get good and proper food, the one you like at least. And so we try to get all our supplies when we get there at Tamanrasset. But as you see, from Algiers to Tamanrasset, there are 2,000 kilometers. Now, of course, to get there, again, it's challenging. Why? If you go by plane, and there are some sandstorms, there's no visibility. So the planes has to come down, and sometimes you have to wait a couple of days. I usually wait like 3 days to get there. But if you're brave enough, but maybe not wise, you go by road, so by bus, and that's even worse, because if you're caught up in a sandstorm, I don't want to be there at least, you know? Alright, okay, so the Hogar, the mountains, are part of the Trans-Saharan belt. And so the Trans-Saharan belt is this big, okay? On the west, in the west, I mean, you have the west, I forgot. I get names mixed. West African Craton, yes. And in the east, you have the Saharan Craton. So the mountains, the Hogar Mountains, are caught up between these two cratons. And you know that cratons are really rigid. So the amount of information we have in the Hogar is quite intense, especially at the borders. And this convergence, this east-west convergence, actually led to a northward tectonic escape. So most of our, we will see, the terrains actually go up, start going upwards. I'm talking like this displacement and this movement has been, of course, observed along the shear zones. Alright, so the Hogar Mountain is actually part of what we call the Tuareg Shield. The Tuareg Shield actually crosses 3 countries. We have Mali, Algeria, and Niger, okay? So the Hoggar, this is its surface, this surface, okay? And this is the Tuareg Shield. So most of the Tuareg, the biggest portion is in Algeria. All right, so for a long time, we actually counted 23 terrains. So I don't know if you're familiar with the term terrain. Yes? Okay. These are like small portions. You see here, like they are, if I had to describe it, I would say it's like a microcontinent. It's a portion of the lithosphere, of the continent. And here, you have, for a long time we had 23, and since 2019, someone named Yejoa added 2 more. I'll try to explain this later. And actually these terrains are usually limited or bounded by shear zones or thrust, yeah. But what you see here in blue are actually what are considered as suture zones. So here we think that there could have been very big oceans, and they were closed during the Pan-African orogeny. As you see, most of the suture zones and the shear zones are northwest. All right? Now, except in this part, most of them are actually northwest to southeast. And you will see now in the next slides that this part of the Hoggar has a very different history compared to the others. So this is like a close-up to how it looks on satellite. And what's really impressive is that you can actually observe those north-south accidents or suture zone. And I was told when I was a student that before we had all this technology, a lot of people, when they used to fly above the desert, they were really happy to get here because they knew where the north was, you know? So this helped them also navigate. And I find that interesting because indeed it's very visible. It's really clear here. All right. So maybe I should go back here. We have classically actually divided the Hoggar into three portions, 3 big units. We will have the Western Hoggar, the Central Hoggar, and the Eastern Hoggar. And this division was made upon 2 lithospheric and like very known suture zones of accidents. So you have the 430 shear zone, and you have the 830 shear zone. The 430 would be here, right? This is the Western Hoggar, and it's separated by the central by this 450 degrees shear zone. So these 3 terrains are well, their names are put here. So Silet, Tizaotin, and Sidani. These 3 represent a specific part unit. It's called here, I forgot to talk about this. So the ones I just mentioned are here, and they constitute the Parisian belt. All right. So if we go from west to east, so going from the West African Craton to Central Hoggar, you will have 2 big units: the Forest Cordillera and the Parisian belt. Then you would move to the central part, to the Central Hoggar, and here you have what we call a lateral, and the Rosarian stripe. And completely to the east, so actually in contact with the Sahara and Metakraton, you have the Eastern Hoggar. It's actually here. It's written right here. So we have this. The story of these is that but they are considered to be juvenile, so Neoproterozoic, and oceanic arcs. And this last one here, it's called Silette, is actually considered to be lying on top of the Latea that is right here. So, the idea behind this, I think, and it's a new thing as well, is now we have two types of terrains. So you have here in the Hogar you have juvenile, Archean, Paleoproterozoic, but you also have crustal terrains and lithospheric terrains. And in this case, as this Silette, when it was overthrust by the Latea, it lost its lithosphere, and it's called now just the crustal terrain. The next thing is that what you see in pink is a very special terrain because it's the only terrain in the Hogar that is completely or mostly, mainly Archean. Like in the rest of the Hogar, you may have like relics, but here it is entirely made of Archean, and it's mostly affected by high temperature metamorphism. A lot of people love to work there because it's easy access, and people it has always been very interesting and curious. So a lot of people we have a lot of study there, which is good. Unlike the rest of the Hogar, for example, here there are very few studies, mostly because it's far from the capital, and I'm not talking about the capital of the country, but the capital of the desert that I mentioned earlier, Tamanrasset. Because on the western part, you do have some paved roads, so yeah, that's nice. But on the other parts, you just have to make your way through dunes and all the different challenges that I mentioned earlier. So here, as you see in white, this is the Latea. So what is Latea? As I told you before, now we are up to 24 terrains, and they are all different. They have a different metamorphic history, a different magmatic history, and they have been deformed in different ways too. But after comparing certain terrains, they saw that a couple of them, which constitute Latea, have similar characteristics. So they consider this as a microcontinent, there's another name, but I forgot. Like it's composite terrain because it has many other terrains. And this one acted as a passive margin. And as I showed you earlier about the Silette terrain, we have the same story here for Silwanut. So Silwanut is very controversial because we have very few studies there. It's far. It's mainly, all the center is made of dunes, sand dunes. So to go there, you really need a lot of motivation or like specific targets. Or maybe just you didn't know how hard it was and you accepted to work there. That's what I did. Yeah. So this part also is considered to be a crustal. It is juvenile. It is oceanic. It is thought to be oceanic, and it is a crustal. Meaning that it lost its roots, its lithospheric part, and it would be lying upon a new terrain that they called Afara. As you see here, Afara. This is an old one. This is an old map. And as you see, Afara was not in it. And what you see also is Aywilen here was not here. So these are the two that Yejua added in 2019. The only problem is that we need geochronological isotopic data to prove these things. Because I forgot to say also, is like the first overall geologic map of the Sahara was made in 1952. Okay, that's kind of late compared to other countries. But knowing that Algeria is dependent only work here, but the Russians also work there, and the Russians did an amazing job. The only problem is that they didn't work everywhere. We have pieces, like parts, that are really well done, and I used those, and I had a feeling I was right there in the field. But the French also have this, I don't know how to express it, but they would always try to give ideas or suggestions about the Hogar without even setting foot there. And that's our main problem nowadays, because we are like trying to fight against the old generation and the new one. The new that actually wants our geology to be Algerian and not French anymore. As I told you, Hogar is not Hogar. The French call this Hogar, but it's Hagar, you know? So there are a lot of studies that are made in this sense to give an Algerian blueprint to our geology. But the problem is, okay, so the structural geology is really well done because that's what people used to do for a long time. And also what I forgot to mention is, given all these hardships and the challenges that we have in the desert, the first geologists were from the army. And that makes sense because they used to stay a long time there. They used to stay like years in the same spot. So they had a really good knowledge of the place, of the geology. But when usually, at least I speak for myself, when I usually go there, it's like for 10 or 15 days. And that's not enough. It's really not enough. But since we pressure you to publish articles, to defend the thesis, you just have to go on and try to do something, you know? So, and this is why Serranut is also very, now when they added this new terrain that's below Serranut, I'm still very curious to know what are the arguments here, you know? Because as I said, they just stipulate things. And for example here, Aurélien, which is right here, so they added, the same author added a new terrain here, stating that there were eclogites here and they were not here. This place, this area was more deformed than this. Okay, they're different, so let's add a new one. This is the spirit. But we need to change this with really consistent data. So in this part of the Hogar, there are two units that have been known and described for a long time. There is the basement, and there is this, I would call it like a metasedimentary sequence. But we don't always find this and the rest. It is mostly known in this area. So the eastern part, okay, the eastern part I told you earlier that it has a specific story. Mostly because what actually characterizes this part is the Morzukian orogeny. So the Pan-African has not been very dominant in this area. And they used to call it a craton, and then a metacraton. Okay, the difference is that it has been stable for a long time, but the Morzukian intercontinental orogeny came and actually gave this structure of the three terrains we see here. And as I told you, this is very also peculiar because you can see they also are oriented northwest to northeast. And it also, so if we go back and we try to understand its place during the Pan-African orogeny, we understand that this was a receptacle, like it gathered. It was like almost, it was not high enough. It was not high enough, but that was good because it got all the morass of the Pan-African orogeny in it. There's a slight difference. So you have Donnet here, Donnet, which is like a green schist facies morass. Then you have Idembo here, amphibolite. But the closer you get to this huge shear zone that we have here, mostly unmortified and metamorphosed morass. And it's in this sense that it's quite interesting. But as it is quite far, it's even farther than the center. So a are really few people that want to go there. But we still found some Pan-African granite suites in the Temple terrain. And yeah, we found some inherited zircon for 1.9, 2.1, and 2.7. Yeah, and there's some old basement, but again, like, it's not maybe quite well identified. Yes, so a lot of people say, like, the works of people actually say that this eastern Hogar was part of the Saharan Metacriton. As if it was a part of it, and it got deformed. We had terrains, and it was like collided with the rest, and we have this structure we have today. Now, maybe you understood now that a lot of the work done, for most part, is descriptive. Okay, we do a lot of structural geology because that's easy. We don't depend on labs. We don't depend on other universities or things like that. So that is well covered. And then we have all between, like the geochemistry, the geochronology, all this. We depend on other foreigner labs, which makes it harder for us. But the good thing is that these days, these last years, a lot of people are actually doing geophysics there. So it's really interesting to see what geologists have said for years, like the different boundaries, the terrains, the shear zones, how this is imaged by geophysics. Sorry. And what we see is that there are some correlations. A lot of it actually coincides, but there are other things that don't, and we will see that shortly. What coincides though is you have these big limits, all right, that are actually even recognized in the geophysics, and these are potential methods that were done here. And then you have first order geophysical lineaments, which are here, right? But they were not mentioned on the geological map. Let me show you. For example, these two. These are first order geophysical lineaments. But if you go back here, there's no trace of those big lineaments. You have just terrain limits. And it's interesting because in the Sewanut here, over here, also the same guy, so Liégeois, actually said there's a suture zone here. I don't know if you remember, it was on the first figure that I showed. But the geophysics don't show anything so major here. What's major is rather this one, which is on the other side of the terrain. And it's interesting because it changes a lot. It allows us to give us a new history to our terrains. Okay, so now I'm going to show you very quickly the different formations we have, the different metamorphisms. I'll be really quick, really. Okay, so as I told you earlier, I talked about the pink terrain, if you remember, and this is it. This is it. And so as you see, the Archean formations are only located in this region. Right. Here is the Archean metamorphism. Again, it's only local here and in this part. But as you see, you have Bertrand et Kaby, 1978. All these are still old data. A lot has been, like, you know when you get so good at what you do and sometimes you get like very intuitive, you don't know exactly, you don't have proofs, but you're intuitive about what's happening. This is what happens, I think, a lot. And same here. So we moved from the Archean to the Paleoproterozoic. And this is like the most common basement that we have. Oh, so I'm sorry, it's not very clear, but okay, so in the legend here you have the amphibolite fascius, which I don't know where it is anymore. I think it's here. I can't see clearly. have the granulate facies, which is mainly here, I guess. And as you see here, is like the green schist facies supposed, and you have amphibolite facies supposed again. So all these are just suppositions. I'm emphasizing on this just to show that there's still a lot to do, and that's why the geodynamic model that we have today, it changes from one author to another. It all depends on how they see the geodynamic of this place. All right, here we have the Ibernine metamorphism. Very interesting. And as I told you, as you can see here, a lot of data is concentrated in here. This is like the most interesting for some. But then also we have that, at least for my university, we have some teams that are just specialized on specific, like I know a team, there are like 20 people working all in this area. And they've been doing this for a long time. But nobody wants to go out of this area and take chances and see what's happening there. And I think that's why maybe we should need more teams to cover more. Okay, all right. Mesoproterozoic. So the Mesoproterozoic is kind of also controversial because a lot of people say that there are no Mesoproterozoic events in this area. But some authors suggest there are. So they just map it here, and I don't know what else to say. This is still a supposition. And again, we have metamorphism. Same authors, same year, same idea. Right, okay. Now the Neoproterozoic sedimentary and volcano-sedimentary rocks. All right, so we have, I'm sorry, on my screen it was much clearer than here. I can't read, right? But this is like the main, this is what they defined as sedimentary and volcano-sedimentary rocks of the Neoproterozoic. But to me, as long as we lack age dating, and as long as we lack some geochemistry, it's hard to. No, thank you. It's hard to be sure. For example, in this area, they talk about upper platform and lower platform. They just give different lithologies to them, but that's all. Like they don't give specific ages or chemical signatures. Okay, so I'm gonna go forward here. So we have the sun subduction magmatism, and it is thought to be usually along the shear zones, as you see here. And again, these last years, a lot of people are interested in this area. So we have a lot of data. I can't read the dates, but it's around 650 million years, mostly. And then you have the high K calcaline granites. Yeah. So in my work, I actually, not just me, other students too, by actually plotting those on geophysical data, we realized that they had different signatures. So all that is actually here mapped as high K calcaline. Our granites are not all actually high K calcaline granites, and we will see that later, which actually makes us think that maybe it's not good to generalize, to have a better idea. Maybe we have to look in deeper and go and sample more of these to see the real difference. Especially when you see that there are different different ages for them. Okay, Merzoukian granites. Okay, once again, we only have those granites in this part, and they're mostly dated between 560 so 75 to 555 million years. Oh, late to post-orogenic granites. So we don't see very big colors here, but they are usually subcircular. Okay, when you look at them on the field, they are subcircular, and they have this rounded shape.